Guys, let us see the iron carbon phase diagram, which is the most important part of metallurgy or the material science. So this is the iron carbon phase diagram. So in the left hand side we'll have the temperature, and here the percentage of carbon here. Okay, so this diagram consists of, you can see that the carbon here, it is going up to like 10 weight percent. Okay, but generally we draw up to 6.67% because that is the composition where we get this Fe3C. Okay, fine. So this is your temperature and the percentage of carbon, and these lines are the lines in the phase diagram, right? So okay, so different phases are marked over here. Okay, so up to 6.67 we have the Fe3C. Now suppose someone wants to draw the iron carbon phase diagram, basically with the help of carbon it wants to make. So basically these lines, whatever these lines are there, so these lines will be extended, right? And since here we talk about carbon, so carbon will have the higher melting point, so it will melt somewhere here when we reach like 100% carbon, so melting point of carbon. Okay, now this is the normal picture, I think you must have seen in every textbook. So this is the temperature in degree centigrade. Okay, and this is the percentage of carbon, so it goes up to 6.7, basically like 6.67 basically it goes. Okay, so the first phase which will be forming here, it will be here, this region is the alpha region, and this is your gamma, then this is your delta, right? Here it is mentioned also. Okay, so this is your delta, this is your gamma, this is your alpha, right? And the temperature, this is the line for eutectoid, right? So this is at temperature 723 degrees centigrade. Okay, 723. In some book it may be 728, 729, so it is approximately 723. Then this temperature is 912 degrees centigrade. Then this temperature is 1400. In some textbook you will find 1401 also. This is your 1493. In some textbook you will find 1496 also. Okay, then this is the last temperature, that is 1538. So that is the melting point of this iron. Okay, so that is for the pure iron. So this line basically talks about the pure iron, right? Because here there is no carbon, right? But if you move here, then carbon starts to get into this iron and the different phases occur. Like here you can see it goes through different phases. In this phase we have alpha plus Fe3C, then gamma plus alpha, then we go to gamma, then we go to delta plus liquid, then we also go to this delta plus liquid, then the final liquid, right? Okay, and this temperature, it is 1147. So this is the point of eutectic. Okay, and this is the point of eutectoid, and this is the point of peritectic. Okay, so there are three invariant reactions which happens in the iron carbon phase diagram. Okay, in the room temperature the phases are alpha plus Fe3C, and here this is the region because here it is the gamma. So from the left hand side it will be gamma plus Fe3C, because in this right hand side it is Fe3C, right? Then it will be gamma plus liquid, this is the liquid, and it will be liquid plus Fe3C. Okay, okay, now we will try to understand the difference between this alpha ferrite and delta ferrite versus this austenite. So alpha ferrite and delta ferrite, so both are of BCC structure. Okay, so both are of BCC structure, and this gamma austenite is the FCC, right? So what is the position of the carbon atom in both BCC and the FCC? So we know that the carbon position is in the octahedral void. Okay, so there are two types of void. One is the octahedral void and another is the tetrahedral void. So in the case of FCC, we can see that the position at the center is the octahedral void, which is shown here, and position over here, this is the tetrahedral void. Okay, in the case of BCC, the octahedral void is at the face center, the tetrahedral void is at this location. Okay, and we know that the carbon sits in the octahedral void. So why it only sits in the octahedral void? In case of FCC, the space, this space is basically larger. Okay, and in the case of BCC, this space is not larger, but the thing is it creates less distortion while this carbon moves, because if carbon will try to sit over here, so there will be more distortion, okay, as compared to the distortion over here. Okay, in the case of tetrahedral site in FCC, it is of smaller size, so that's why it doesn't go over there, and also it will have to stretch the bonds also. Okay, and that you can understand through this radius ratio. So in the case of this FCC, for this octahedral void, the small r by capital R, small r is the size of the void divided by the capital R is the size of the radius, okay, of the iron atom. So r by r, so this you can understand like the size is 0.414 times this r, as compared to this tetrahedral void, which is 0.225. So it is larger, this is 0.414 is larger, so that's why in FCC it sits in the octahedral void. Next we see in the case of BCC, so the radius ratio, if you see, the radius is only 0.155 times of r, and here this is 0.29 times of r. So we can see that this is larger, but then also the carbon will sit in the octahedral because it will create less distortion. Okay, see, in the case of FCC, the octahedral site is bigger than tetrahedral. In the case of BCC, tetrahedral sites are bigger than tetrahedral. See, although BCC has more total room for interstitial atom, FCC has the largest particular interstitial site, octahedral. This can have a large impact in interstitial solubility. So it affects on the solubility, like the dissolving of carbon. So iron less than 0.008 weight percent in alpha ferrite at room temperature. Okay, so it is trying to give you the feeling that in the case of FCC and in the case of BCC, so what is the solubility difference of this carbon? We can also see from this one that alpha, which is over here, it goes maximum over here, right, and this value is 0.02, and at room temperature it is 0.008. Okay, and if you see in the gamma, the carbon percentage it can go is 2.14. So here 2.14 and here 0.02, right? So it is around 100 times more, right? You can say. So steels. Okay, now in this phase diagram, this is the reason we generally call it as steel up to this 2%. Okay, from this 0 to 2% we call this one as steel, and beyond this we call it as cast iron. Generally, so the steel is called basically up to 2.14%, and cast iron it is called beyond this 2.1 4%. Okay, so this is called as, it contains this alpha ferrite and Fe3C at room temperature. It is talking about this phases. So we have here alpha plus Fe3C is there, so here also it will be alpha plus Fe3C. Okay, cast iron more than this. Okay, now if you see the structure of alpha ferrite and gamma austenite, okay, so alpha ferrite, it is BCC, right? So it looks somewhat like this, and this FCC, it looks somewhat like this. The difference you can see that in this grain only, this is the grain, so we are seeing some straight lines. So these are basically the twins. These are twins. It may be annealing twins or the mechanical twins, depending on the operation which has happened. So these are basically annealing twins. Generally annealing twins are more, because if there is no work it has been happened. The mechanical twins happens because of some work which you do over there, and this is your alpha ferrite. Okay, now again we are trying to understand through the phase diagram. So this is, here it is gamma. Okay, and I told you that this is the eutectic point, this point A. So here eutectic, we know that one liquid should give two solids. So here we can see that liquid is there, so that is getting transformed to this gamma plus Fe3C. So that's what it is written over here. Now if someone asks you the composition for this, so for gamma you will stretch this line to this left hand side, so it is here 2.14, and for this Fe3C you will stretch up to here, so it is 6.67, it is 2.14, right? It is given 6.7, so that is approximate, so it's actually 6.67. so if you write 6.7 also, it's correct, don't worry about that. And the next point is the point B, that corresponds to this eutectoid reaction. So in case of eutectoid, I told you that one solid gives two solids. So this is your gamma, this is in solid form, so this, it is giving you alpha plus Fe3C. That's what over here. Okay, now here it is also talking about the phase change. So this is the gamma which is in the solid, so it will have the grains which are of gamma, and this transform into alpha plus Fe3C. So this alpha plus Fe3C looks similar to this lamellar structure which we found in the case of eutectic. So this is basically alpha, this cyan color is the alpha, this red color is the Fe3C. Okay, so this structure is called as paralytic structure. Okay, so here is the macro structure it is trying to show. So this white one is the alpha, and this black one are the Fe3C. Okay, so this is what the perlite it looks like from austenite. Okay, now how it forms. So basically it is described like, suppose we have this gamma over here. So at some point, okay, at some point what happens, the carbon which is in this gamma, which is in dissolved form, so that moves to certain location here. Suppose it moves here, so it will increase the carbon content over there, and to form this Fe3C we need 6.67%. so we will increase this carbon over here, and it will make this region richer in carbon. So this will form something like this. Okay, so this, it forms Fe3C. Okay, so next thing, the region just adjacent to this will be lacking this carbon. That means low amount of carbon will be there. Once the low amount of carbon it will be there, so it will transform to alpha. So we know that alpha contains less amount of carbon, so this becomes alpha. So similarly again, a patch of this alpha Fe3C form, then we get like this. Okay, so this is what it is trying to show, that so this is your cementite Fe3C and this is your ferrite. Okay, it has formed. Okay, and here it is also showing that the carbon, it diffuses from this ferrite region, means this region, to this, because here we want to increase the carbon content, right? No problem. Okay, now this is your point of eutectoid, right? So just to the left it will be hypoeutectoid and to the right it will be hypereutectoid. So we'll discuss this hypoeutectoid steel, right? So this is the steel. Suppose this blue line it is given, so from this 0 to, like, it is basically 0.008, so 0.008 to 0.76, this composition is 0.76. okay, so up to here we get this hypoeutectoid. And what will be the structure change? So this will be gamma first, then at this point the alpha will start precipitating at the grain boundary, so it is given, this is your alpha. Then below this, so it will up to this point, this line and above, so more amount of alpha it will form. Okay, then in this region, since alpha it has formed, now the remaining gamma, so remaining gamma will transform in this fashion, alpha plus Fe3C. So this will be your alpha plus Fe3C, and the extra, it is the alpha region. Okay, so this region it will contain basically alpha and also this perlite. Okay, so what happens basically when we do the cooling? So here if you see at this point, I am drawing in a broader way, this is 0.76, this is 0.02, right? Now we are doing the cooling, right? So at this point we have here gamma, and at this point the alpha starts to precipitate. So what is the composition of alpha which starts to precipitate? It will be this, right? So again we do the cooling, so this alpha will be of composition this, and gamma will be of composition this, right? Again do the cooling, so alpha will be of composition this is alpha, right? Left hand side, this is gamma. So again, so once it comes to this location, so alpha will be of this 0.02 and the gamma will be of 0.76. so the remaining gamma below this temperature will transform from this line, this is the eutectoid line. So that's why we will have the alpha as well as the eutectoid perlite. Okay, so this is what the microstructure looks like. So this is your alpha, this white color, and this black one, it is the perlite. Okay, now if someone asks you to find the percentage of this alpha and this gamma in this region, because in this region we will have here like this, let me draw it. So this will be your alpha plus gamma, right? So at any point if someone asks you to find, so this is your R and S, so we need to find W alpha, right? So alpha, it is in the left hand side. So why it will be left hand side? Because this is the region of alpha here, so it is in close contact with alpha, so left hand side it will be alpha, right? So left hand side we have the alpha, so this we will find by R divided by R plus S, right? So this, sorry, yeah, S divided by R plus S, that's what it is given. And W gamma will be R divided by R plus S, or we can just subtract it with 1, because these two ratio is equal to 1 if you add these two, right? Now here, if at this point, what will be the composition of this alpha? Here it is given perlite, then alpha, then Fe3C. Okay, so here is a trick. Here is a major thing. Like suppose if the question asks you to find the amount of perlite, then we know that at this point only the perlite forms, right? So we'll take the tie line up to only here. But if it asks you to find this alpha as well as this Fe3C, so we know that since it is combination of alpha and alpha plus Fe3C, that means there is total amount of alpha over there, and gamma sorry Fe3C is there. So we'll take this complete line. Okay, so here it is asking you to find this perlite. Okay, and this perlite, here it will be the perlite, right? So this region will be nothing but alpha plus this perlite. So this perlite we can write here like capital R by R plus S. Okay, capital R by R plus S. Okay, no problem. And now we here it is asking you to find this alpha and Fe3C. So alpha it is in the left hand side, so S will be this complete S over here, right? So I think, oh sorry, that this S is not the complete S. This S will be up to here, like 0.76 minus this composition, that is C naught. Okay, now if you want to find this alpha, then it will be S, this complete length S divided by this R plus S, or Fe3C 1 minus W alpha, right, which is there. Similarly for hypoeutectoid, so this is the microstructure chain. So it is the gamma initially, then at this point some amount of this Fe3C will precipitate, because this is the line where it is in contact with Fe3C. So some Fe3C will first form, right? This is your Fe3C, then this Fe3C will grow, right? So again once it reaches this point, so this is the composition of gamma it reaches, and this is the composition of Fe3C. So gamma, rest gamma, it will transform like the eutectoid, that is the perlite. Okay, that's what it is given away. If you see the structure, so this whitish region is the Fe3C and this blackish is the perlite. Okay, now here also if you use the tie line, so this tie line if you use, we will be able to find this gamma and alpha 3C, right? So this gamma, so gamma is in the left hand side, so it will be like x divided by v plus x, that is given. For Fe3C it will be 1 minus this. Okay, or you can also write like v divided by v plus x. Okay, now at this point if someone asks, and if you want to find this alpha and Fe3C, first you see, so alpha it is in the left hand side, so it will capital X divided by v plus x, it is given, and Fe3C it will be 1 minus this, or you can write v divided by v plus x. And this perlite which is given here, now see once we reach this alloy, so we know that perlite is forming over here, right? So perlite is forming over here, so that means the tie line will be starting from this to this only, that is A B C. So here it will be ABC. So this weight fraction of this gamma in this, because it will be perlite plus this, so here the structure will be like perlite, here it is perlite and here it is Fe3C, right? So we need to find for perlite. So perlite it will be in the left hand side, so it will be something like this. it will be your this capital X divided by, okay, capital X is also written, I have written like BC divided by this AC, okay, or AC we can write it like AB plus BC, okay. And this is the point of eutectic at 4.3 weight percent carbon, right? This is the eutectic form it is forming. And these are some of the questions. So okay, so let us try to solve this question. So for a 99.6 weight percent, that is iron 0.4 weight percent steel, at a temperature just below the eutectoid, determine the following: the compositions of Fe3C and ferrite, the amount of cementite in grams that forms in 100 gram of steel, the amounts of perlite and proeutectoid ferrite alpha in the 100 gram. Okay. So first question is the compositions of Fe3C and alpha, right? So this is your 0.4. So 0.4 will be between this 0 and 0.76. So that means it is case of hypoeutectoid steel, right? What is this point? So it is telling you just below this eutectoid line. So it will be the point just near to this line, right? In the lower direction. Okay. So this is your composition of alpha, which is 0.02. Composition of Fe3C, it is 6.7. It is touching over here, right? Using the lever rule with the tie line shown. So weight fraction of Fe3C, right? So since it is talking of this complete Fe3C and this alpha also, right? So we'll take the complete tie line. Here it is not talking about this perlite, right? So it will be a complete tie line. So it will be, since Fe3C is in the right hand side, so we'll take the left one, that is R. So R divided by R plus S. So what is the value of R? It is C naught minus this C alpha, and this complete length is C Fe3C minus this C alpha. So it is 0.40 minus 0.022, 6.7 minus, so it is 0.057. Fraction of Fe3C is there. So what will be the fraction of, okay, okay, so it has been converted at, suppose in the case of alloy, it is totally 100 gram of alloy. So out of this 100 gram, so it is 0.057 fraction, weight fraction of Fe3C. So what will be the weight of that? So simply multiply it with 0.057. Okay. Now using the, now that is the question B, I think, right? B we have solved, no? B, amount of cementite, okay, we have solved. First we found what is this Fe3C and this. The amount of perlite and proeutectoid ferrite. So we need to see for this perlite also, right? Option C. So now once we have the perlite, so this is the perlite point. So this will be the line, okay? So this will be the boundary line. So we will make this tie line, okay? No problem. Now what will be the amount of perlite which is forming? Okay, so this is the perlite here. In this region it is alpha plus perlite, right? So perlite is in the right hand side, so we'll take this V divided by V plus X. So it is 0.512. So weight fraction of perlite is 0.512, right? Now, so what is the amount of perlite? It is 51.2 gram. Okay, so we are able to calculate easily, right? Now what happens with alloying with other elements? So basically when we do the alloying, so generally most of the element increases the strength. Okay, so I think here it is given. Okay, so it talks about what happens to the eutectoid temperature. So basically it increases the eutectoid temperature in most of the cases. Only some cases it decreases. So why it decreases? Because see, nickel, manganese, these are of FCC, and uh, the eutectoid transformation starts from this FCC, right? You can see this is your gamma, that is FCC. So what will happen if you add this nickel and manganese? So this gamma will be stabilized over a lower temperature, because this is also FCC. So once it is stabilized at lower temperature, that means the eutectoid temperature will go down. But it happens opposite if you add this element titanium, molybdenum. So these are BCC. So it tries to lift the alpha region to the top because it stabilizes. So it stabilizes to higher region also, because alpha is stable at room temperature. So it tries to push it forward. So that's why the eutectoid temperature it changes, right? Next, okay, so with the help of, suppose carbon content of eutectoid, does it change with addition of elements? Yes, it changes, because you know, with weight percent of alloying element, basically the point, the carbon concentration at which this eutectoid transformation happen is lowered. Okay, so it happens because the effect of this molybdenum and other elements is similar to somewhat similar to carbon. That means the effect which this carbon produces, that can also be produced with small fraction of adding of some other elements in the material. Okay, so that's why it basically decreases the carbon content at which the eutectoid transformation happens. Okay, so this is the summary. Phase diagrams. Okay, yeah, we have different reactions: hypoeutectic, eutectoid, peritectic, like this. This is the iron carbon phase diagram. Again it is shown. Okay, austenite, ferrite. Austenite is the FCC, ferrite is the BCC. Then this is your martensite. Martensite is also similar to BCC, but only thing is, because of this carbon entrapment, the C axis, one axis, it elongates. Okay, now these are some of the practice problem, I think, so you can do by yourself. Okay, and if you have doubt, then I can also help you with this. Okay, so these are different questions, you can try by yourself. Okay, so hopefully it will help you for your understanding. Okay, so thank you.